So, here's the time. Okay, let's see. Okay, so we are doing number 3 today. So, here is the problem. So, we need to first determine the speed of the block before it hits the spring. So, part A, speed of the block. So, we see that the block is on an incline. So what we can do is we can first find acceleration, because we can set up for the block F equals ma, and our F will be our FGX. So we have FGX equals ma, and then what we can do, so FGX is mg sine theta, ma, mass cancels out, so we have gravity, sine, and our theta is 30 equals a. Just plug that in. .9 meters per second squared equals a. So now that we have that, we can find the speed right before it hits the spring. So we can go ahead and set up common form. So delta x equals vf squared minus vi squared over 2a, and we know that it starts from rest, so there's no vi, and then it tells us that there's a delta x. There's 6 meters in between the block and the spring, so we can go ahead and put that as our delta x, and we can use our a that we found to plug it in. So then it's 4.9, so then it becomes 6 times 9.8 vf squared. Square root. Okay. Alright, so now for part B. So it's asking us to calculate the time it takes for the mass to travel the 6 meters. So we can go ahead and use our distance formula. And we know that it starts from rest, so there's no vi. Our delta x is 6. And so then that equals, and we can use our acceleration again. that is our time. Okay, so now part C. Determine the distance the spring has compressed when the block comes to rest. Okay, so what we can do is we can set up PEI is equal to PE spring final. And we know that PE is equal to mgh, and the function for PE spring is 1/2 kx squared. So now we have to go ahead and plug everything in. But for height, we need to, so this is our starting height. And we're just gonna call this x. So we have to find our height, right? So it's gonna be sine of 30, h equals sine of 30 times x plus the 6. So that's what we can use for height. So we still have mg, and then our h is, I'm going to move it around, but x plus 6 sine 30. And that is equal to 1/2 kx squared. Okay, so now we can go ahead and plug everything in. Mass is 20, 9.8 gravity, x plus 6 sine 30, and then that's equal to 1/2, 200, that's a mass. 1/2 200 x squared. Okay, so now we need to simplify this side. So you have to distribute to the x and the 6. So first let's solve 20 times 9.8 times sine 30. So 20 sine 30 is 98. So you get 98x plus, so 98 times 6 plus 588. And that's going to be equal to 100x squared. So now what you can do is you can move both of these to the right side. So you get 0 equals 100x squared minus 98x minus 588. That way you get a quadratic. And then with this, you can plug it in to quadratic solver. And then we can go ahead and plug it in. So 100 is our A, negative 98 is our B, and negative 588 is our C. So you get x equals 2.96, and that's meters. So that is how much the spring is compressed. Okay. Okay, so now on to part D. Okay, so is the speed of the block at maximum at the instant the block strikes the spring? So no, it is not, because so it's not, because if the spring weren't there, then it would have more distance to travel to keep okay, let me start over. So the block is not at its maximum speed because it is accelerating. And since it's accelerating, that means it can keep getting faster and faster, correct? But since the spring is here, the spring slows it down and keeps it from accelerating all the way down the ramp. So let's use some math for that. So let's say, okay, let's just use the distance that we found for this. I know it's not the full length of the ramp, but let's just use that to find a different speed if the spring weren't there. So we can go ahead and again, really we're just gonna do this, but instead of 6, it's gonna be 6 plus this. So we can do, so delta x equals vf squared minus vi squared over 2a. Again, no vi because it starts from rest. So our delta x is going to be 6 plus 2.96 is equal to vf squared over 2, and our a again, 4.9. Okay. Okay, so as you can see that the VF has increased compared to when it hits the spring. So to reiterate what I'm trying to explain, it's not at its maximum because the spring is there. If the spring were there, then it would be able to go this whole length of the ramp and then meet its maximum speed for this scenario. But since the spring is there, the spring slows it down and keeps it from reaching its maximum speed. Okay. Okay. Part E. Okay. Part E says if the mass is now increased to 40 grams, so doubled, would the answer to part A, B, and C change? Justify your answer. Okay, so part A was looking for the speed. So for part A, if the mass had increased to 40 as opposed to 20, the answer would not change. So as you can see, first we had to find acceleration, and mass is in there, but then as soon as you expand it, because the force that's acting on the block is FGX, mass cancels out and is not needed in the equation. And then even to find the final VF, mass is nowhere in here. So for part A, the answer would not change. Again, because in the functions that we used, yes, mass is there, but it cancels out. So really it has no effect on finding the acceleration. And then to find VF, mass is nowhere in the equations, so would not affect. Okay. Part B was finding the time. So again, mass is nowhere in this equation, so it would not change. And since this, the final VF isn't changing, that means time wouldn't change. Because, so again, mass cancels out, and then mass isn't needed, so that's not changing. And since the VF isn't changing, and mass isn't needed in this equation, time wouldn't change. So part B, no change. And then part C. Okay, part C, determine the distance the spring has compressed when the block comes to rest. Now, this is where mass will change it. So as you can see, mass is part of the PE function, and there's no way it can get canceled out. So it would change. So instead of this being 20, this would be 40. So this would all increase. So we can go ahead and work that out just to prove it. Okay, so we're gonna start from this line right here. So it'd be mgx plus 6 sine 30 equals 1/2 kx squared. Okay, so now our mass is 40, and then 9.8 x plus 6 sine 30 equals 1/2, and our k was 200. Squared. Okay, so again, we have to distribute it to the x and the 6. So let's find 40 times 9.8. Sine 30. So it's 196x. And then plus 1176. And then that's gonna be equal to, again, 100x, and then again we're gonna move everything over, so it's 100x squared minus 196x minus 1176. And then let's go ahead and plug it into our solver. So 100, and then minus 196 minus 1176. So now our x is 4.55. So as you can see, the compression has increased when the mass has increased. And again, that's because when you look at our PE function, mass is there and there's no way you can cancel it out in the function. Okay, finally moving on to part F. Okay. Okay, so part F, if the coefficient is, so now there's friction. That's basically what it's saying. Well, actually there's friction up until the spring. Okay, and the mu k equals 0.15. So now it wants us to recalculate part C. Okay, so we're gonna go ahead and set up our energy just like we did with part C. So PEI, but this time since we have friction, it's gonna be minus the work of fric, and that's gonna be equal to your PE spring. Fine. Okay, now we can go ahead and expand everything. So mghi minus delta x times fk is equal to 1/2 kx squared. Okay, so now again we are going to need to use this right here. Again, because, I mean, PE doesn't change, so that would be, or not this line, sorry, this line. Again, because we need to find the height, so sine x plus 6. Okay. So mg x plus 6 sine delta x. And then for f of k, that is f of n times mu k 1/2 kx squared. Okay, so we can go ahead. So we have to keep expanding this though. So delta x is 6 plus the x again because the block does compress the spring. So there is friction here. I just meant there's no friction on the spring. Okay, so for delta x, that's x plus 6 again. And then our f of n is equal to fgy. So f of n is equal to fgy. Draw it out. So this is our f of g. This is not gonna. You have fgy, and then your f of x, or fgx, sorry. Okay, so your f of n is equal to your fgy, and fgy is ng cosine theta. So we can use that for f of n. So ng cosine r equals 30, and then mu k is 0.15. Alright, so now we can start plugging everything in. So 29.86 sine 30 minus x plus 6, 29.8 cosine 30, 0.15, 200 squared. Okay, so now we have everything. So now it really comes down to just like algebra. You have to make sure you are distributing everything correctly. So, okay. So you just have to make sure you're distributing everything correctly. So for this one, okay. This part you have to make sure because there's a lot more, and you just have to remember to distribute to the x and the 6. This time it's cosine 2, so cosine 30. And you also have to remember to distribute this negative. Oops. Okay, and so now combine like terms. So that's this one And this one, and then this one, and this one. Okay, and then again, we're just gonna move everything to the right side. 100x squared minus 72.54x minus 435.24. And then we are going into our equation solver. So 100, oops. Okay, 100, and then negative 72.54, negative 435.24. Solve. And now our compression length is equal to 2.48 meters. Okay, let's see what. And so this is our ending time.